Hi, I'm Samir once again. I talked about what I do at AWS. I'm going to pass it back to Roneel to continue.
Cheers, mate. Thank you. So, in terms of what you're going to be talking about today, the primary things are actually going to be how to actually monitor slow running SQL statements on Postgres. Some of the ways of actually looking at logs in Postgres and how we can actually go in and do session monitoring and sampling wait events on Postgres. And then finally, we'll finish off with a case study on identifying bottlenecks using wait events as well. So if you look at Postgres allows you to actually go through and log slow running queries by setting a threshold for a parameter called as log duration statement. And you can also use the extension on Postgres called as PG statements to identify average and maximum sort of time taken to actually execute some of the top running SQLs on Postgres. And the PG statements extension also provides other useful information onto the users, like things like your buffer hits that are there, your disk file writes that are actually getting occurred, your temporary file usage, and on top of a number of the CPU waits that we'll actually see here as well. And your workload can typically get bottlenecked by the range of parameters that are actually on the screen, things like CPU, I/O, your and it can also be your object level weights that are there. And typical examples of CPU bound workloads are those with high concurrency, and where the working set fits inside the shared buffer as well. IOs, on the other hand, is the most common bottleneck for some of the large databases, but where the working set actually fits, or there's a small set of pages in buffers are modified by concurrent backends that can also suffer from buffer contention, or even actually get lock contention for a hot row or hot page. Now, whilst SQL monitoring techniques, covered, provide you with information about the resource usage that we actually see, you could actually have situations where you can have things like two bad queries that are running in completely separate time windows. An example could be actually have got two queries that are running, for example, for 30 minutes that are actually contending for certain resources, but they don't collide. They don't run at the same times. You might never see them causing any problems. They're basically running in their own times, basically going away and happily being able to run through. Now, let's look at the monitoring using PG static activity. Now, PG static activity gives you the current state of each of the backend processes along with the query that's currently executing. And it also gives you kind of the age and the query of the related transactions that are there. And it will also provide you with information about wait events, such as things that it's currently waiting on, right? Such as I/O, lightweight locks, or you could actually have your heavyweight locks there as well. And things like your state and your wait events are actually there on PG static activity. And let's look at the age and the event in more detail. So if you actually look at a backend process that's actually here. So common, usually what you'll have is the transactions that you're actually running usually actually going to be either in active or idle states, right? This is basically an active is where your query is currently running. Idle is where it's actually gone in and run, and it's actually waiting for the next instruction. Now, the transaction, the state that actually causes most of the pain is where you've actually got idle in transaction. Now, this is because typically in my experience being either it's an application bug or a third-party API that's actually there. It basically means that you've actually gone in and opened a transaction, you've gone in and run some activity, you haven't actually just gone in and closed it now. You haven't actually issued a rollback document. Now, this just means that the session, it will actually go in and hold on to the state or the locks that's currently there until the end of the session. And it can also go in and block actions like, or maintenance actions like your auto vacuum as well. Now that in turn will actually cause additional performance problems because you can actually end up having high IO or have poor buffer utilization, and finally also increased risk of wraparound that will be actually there as well. So if you actually have or see a situation where you actually constantly see transactions that are sitting in idling transaction and they're there for a few minutes, right? It is normal to actually see idling transaction for a few seconds or so if once the transaction is running. But if you actually see those running for a while, that actually is a sign for to actually look deeper into the database as well. Wait event type and event types and kind of the state values can be seen by querying the PG stat activity view on Postgres as well. And the wait event and the state columns are independent, right? So if a backend process is in the active state, it may or may not be waiting on some sub event that's actually there. And if the state is active and the wait event is not null, it basically means that the query currently is being executed. So it's been executed, but it's actually currently getting blocked somewhere in the process. So the wait event type provides information on the nature of the wait and the details of the sessions that the session is currently waiting on. And it's actually indicated by the wait event column that you'll actually see in the in PG stat activity as well. And a session of active state can go through different wait types for the life of when the query is running. For example, I update query might actually wait for a data file read per se to read data from storage. And then it might actually go in and wait for a lightweight lock on a buffer, right? As an example, in order to modify it. And whilst committing the update, the session may actually go in and wait for a lightweight lock on, say a well insert. Or if it's actually waiting for any other process, it's a heavyweight lock that's actually there. So typical wait events that causes contention out of type IO, your lock or lightweight locks that you'll actually commonly see in your Postgres database. And Postgres also uses different types of locks to prevent against concurrent modification to a given resource by two backend processes as well. And the backend process wanting to wanting to access a particular resource must first acquire a lock on that object itself, like calling dibs on it. So if another process is actually currently holding onto holding a lock on that object, it actually goes in and adds itself to the waiting queue or the loop for the queue to wait for the resource that's currently actually getting locked. And basically, as soon as that lock gets released, this new resource or the new session will go in and finally acquire that lock as well. Finally, PG locks view gives you access to information about the object logs held by a open transactions within the Postgres database. And PG logs contains one row per active lockable object. So, for example, if you actually have got logs that are actually there, actually you will see one row in if you actually query PG logs view. And the lockable view may also appear many times for multiple transactions that are holding or wanting to hold locks onto the object as well. An object with no current locks will also not appear in the view as well. So this is, if you actually the locks, this is it that you actually can see. Now you can use the PID column within PG stat activity to retrieve other information about the session holding or requesting a lock using PG locks as well. Now, here's a summary of a table that basically shows you the lock modes that you'll encounter. And as you can see, not all locks are actually compatible with each other here, right? You can actually see an example of shared exclusive row lock that's actually here, which means that it does not conflict with a operation like exclusive or exclusive lock, but it'll actually lock through lock through itself if it actually there is an operation that's actually blocking it. You want me to change the mic? This one is off. Okay. Now that means that like whilst normal operations like vacuum and maintenance operations are running on a table, it'll still be able to go in and run a select, update, delete, or update kind of a statement. But you won't be able to modify the schema definition of the table, or run things like concurrent modification or concurrent maintenance operations on the same table at the same time as well. Now that we've actually looked at some of the wait events and the lock types that are there, let's see how concurrency can actually go in and affect performance as well. So if you actually have a highly concurrent workload with several hundred or thousands of active sessions that are there, it'll affect resource utilization, and you can typically observe it at the operating system level as well. Now, either in the form of IO latency or some sort of resource blocks that are actually going to be there, or things like a drop in free memory, increase in CPU usage that you can actually going to observe, and that will in turn basically show an increase in the number that we're actually seeing, corresponding with the CPU utilization on the database. Now, this is basically done using sampling on PG stat activity. So let's actually go and look at sampling in greater detail. So in a highly workload with high number of queries that you will actually see on your database, you won't actually be able to get to the root of the issue by just looking at PG stat activity, right? You actually need to go through and understand what kind of led up to that event as a result. So when you actually have a high CPU and things of that sort on the database, you'll need to look at historical data that kind of led up to your event. And one way of doing that is basically sampling PG stat activity. Now, sampling gives you a acute view of your workload. Instead of going through and adding statistics for each component, it goes in and examines your system activity at particular times across all components that you're there. And the only samples that are available, we don't actually go in and have full measures of it, but each instance, however, provides a thorough overview from a user call all the way to your system calls, in terms of what's occurring at a particular point. So averaging those samples for a given period of time actually gives you that average activity for the time period. And what it also does, it actually gives you an aggregate of the multiple data points that are actually there, to actually average out the noise. And so you can look out for queries where tuning efforts should actually be focused as well. Now, we discussed how you can actually sample PG stat activity and the slice of data actually captured by different dimensions also in our PGConf talk in India last year. So you can actually go in and view that on YouTube as well. So without spending much time on the topic itself as well, we want to show you, how you can actually go in and look at average active sessions by state. And you can also find out, where if your CPU or if your workload is actually CPU bound, IO bound, or there's other lightweight locks that are actually holding things up using wait events as well. So if you sample PG stat activity and PG stat statements, you'll see you can actually get a holistic view of your workload, right? It tells you over time running what the wait events that are actually there at a particular point in time. So for example, you actually have the setting at this particular point in time and see it's not running, or you can actually see what kind of led up to that, or what are the kind of wait events that are actually there at that particular point in time, which is why sampling is so important. And it also allows us to actually go in and correlate average activity with how many times a particular call is actually made as well, right? For example, if you look at this insert event, it basically tells us how many times that event also kind of led up to that particular event as well. Now, with that, I'll hand over the mic to Samir, shooting scenario with you as well.
Thanks, Roneel. I know we are behind time a bit, and we got 2 minutes to kind of wrap this up, but I do want to talk about this very quickly. We talked about another use case of how when you're sampling these wait events from pgstat activity, and when you use that to build this kind of view that Roneel talked about earlier, where you get to see how the trend has been in the wait events. We talked about that in great length at PGConf India. And what we did for this talk is we used a different use case. So we built a different scenario, different use case for that, where we see that the throughput, the number of transactions that could be processed by the system, that drastically dropped, almost 10x, all of a sudden. So we decided to take a look at the other matrix that we sample. So we see that the CPU utilization for that same period also has reduced. So that is a bit confusing, right? The CPU utilization is lower. So what is causing this degradation? It looks like less amount of work is getting done. And then we go and look at number of backend sessions. So number of connections is kind of static, but we see an increase in number of block transactions. And all this is because we are also sampling other metrics, right? pgstat statements, we are sampling pgstat databases, pgstat activity, and we are sampling it not just the number of connections, but also their state. So we see number of block transactions has increased. Then we go and look at the sample wait events. By the way, if you're wondering, this is not something that I have plotted myself through Excel sheets. This is something that's available to our customers on RDS and Aurora. It's called Performance Insights, but it is something that you can also build yourself if you're sampling pgstat activity and wait events. Yeah. So this is where we see that there are two wait events that show up almost at the same time when we see performance degradation. And these are transaction ID lock and tuple lock. Now, transaction ID lock happens when you have a lot of concurrency in your workload, which is trying to work on the same row. You have two different connections trying to update, insert, or acquire a lock on the same row at the same time. And it's basically like one session tries to acquire a lock. It's trying to do the update. The second session, when it tries to acquire the same lock, it is going to be blocked, referring to the table that Roneel was talking about earlier. And then that's how we get to the transaction ID lock contention. The tuple lock contention is also related to two different sessions trying to do select for update or select for key share. So that smells a lot like row lock contention. So we went and tried to look at SQLs that were running, so top SQLs at the same time, and we identified there is this new query that is pretty much did not exist before. And this smells like some application change. Yeah. So we went and looked at PG lock. PG lock is where all locks are stored. So we could use PID column to identify. We first went and scanned the pgstat activity for the query, use the PID column to look for all the locks that it is waiting on. You can use granted column to filter on the locks that it's waiting on. We identified there is an exclusive lock it's waiting on. We used PG blocking PIDs function to identify what are the other sessions that's blocking my connection. And then we went ahead and tried to identify what are the locks held by those blocking sessions. And we found out that there is indeed a row lock contention. And all right, we were able to investigate this further. We identified that it was happening because of some application change. We went ahead, worked with the customer and the developer to fix that. But the recommendation here, all right, PostgreSQL has got deadlock detection mechanism. What you need to make sure is that you set deadlock timeout, and based on that, PostgreSQL will make sure that it looks for deadlocks and kills sessions that are participating in that cyclic dependency of these lock waits. And you can also log the lock wait events. As a good practice, make sure that you're sampling pgstat activity, you're sampling other statistic. When you sample pgstat activity, you're taking pictures. When you put them together, it's like building a motion picture about your database history. And then you can add additional information by logging key events like slow running SQLs, checkpoints, and using that information, you're basically providing sound to your motion picture. And that's the way you can go back and look at what has happened in your database, debug performance issues. All right, the same QR code once again. If you're interested to learn more about AWS, that's a wrap. Thanks, everyone. Thanks for being patient with us.
Thank you.